Welcome back. Okay, today we're tackling a mathematical tool that is honestly basically a superhero in the world of physics. I'm talking about dimensional analysis. It's an absolutely incredibly powerful approach for solving complex problems and checking your work. But, as we all know, every superhero has their kryptonite, right? If you just assume that every formula you derive through dimensional analysis is 100% flawless in the real world, well, you're going to fall into some major traps. So while it's a fantastic tool, it definitely has a few hidden weaknesses that are absolutely crucial to master, especially if you're looking to ace those upcoming physics exams. Let's uncover these blind spots together.
Okay, let's dive into this roadmap. Today we're going to cover, first, the achievements of dimensional analysis. Second, its failure to identify constants. Third, the three-variable limit. Fourth, we'll look at trigonometry and log functions. And fifth, the mystery of scalar versus vector quantities.
Kicking things off with Section 1, the achievements of dimensional analysis.
Now, before we start critiquing our superhero, we really need to remember its immense utility. It has three incredible superpowers. First off, it allows for seamless conversion between systems of units. Like you can actually prove that 1 Newton in the SI system is equal to 10 to the power of 5 dynes in the CGS system. Or that 1 joule is exactly 10 to the power of 7 ergs. Pretty cool, right? Second, it lets us check the correctness of given formulas. And third, you can actually use it to derive entirely new physical formulas from scratch. Now, quick test. Do you remember your fundamental units? We're talking mass, length, time, temperature, current, amount of substance, and luminous intensity. Knowing how to apply these is absolutely essential, because they form the literal bedrock of physics problem solving.
But here's where things get a little tricky. Consider this ultimate false positive paradox. Take the actual correct second equation of motion that you all probably know by heart. S equals ut plus 1/2 at squared. Now compare that to a completely fake equation. S equals ut plus 1/9 at squared. Imagine a student who hasn't really studied just guesses that 1/9. Well, here is the problem. Because 1/2 and 1/9 are pure numbers without physical dimensions, dimensional analysis sees these two equations as exactly the same, literally identical. If you check the dimensions on both sides of these equations, they balance out perfectly to length. So, dimensional analysis just cannot tell the difference between the correct half and the completely fake 1/9.
Which brings us to a golden rule you absolutely need to etch into your memory for exams. And it goes like this. If a formula is dimensionally correct, there is no guarantee it is generally correct. But if it is dimensionally incorrect, it is absolutely generally incorrect. Examiners absolutely love to test this exact logic. It's basically a one-way street. A dimensionally correct formula just means the units balance out, right? It doesn't guarantee the physics is actually right in the real world. But if the dimensions of mass, length, and time don't match on both sides, you can confidently take that formula and throw it straight in the trash.
Moving right along to Section 2, the failure to identify constants.
So, the really crucial point here is that dimensionless constants, we're talking pure numbers like 1, 2, pi, or Euler's number E, which is approximately 2.718. These completely lack physical dimensions, and during dimensional analysis, they remain entirely undetected. Basically, our hero treats all pure numbers as identical invisible ghosts. This means dimensional analysis can tell you exactly what physical variables are in a derived formula, but it can never ever deduce the exact proportional values or the constants attached to them. Whether the constant is 1, 1000, or, 0.07, the method just treats them all exactly the same.
That brings us to Section 3, dealing with more than 3 variables.
Let's see how this mathematical roadblock works out in practice. This brilliantly illustrates the point using Poisson's formula for the volume of a liquid flowing per second through a tube. When we construct a formula using dimensional analysis, we look at what factors the quantity actually depends on. So we have step 1, the pressure gradient, which is pressure per unit length. Step 2 is the viscosity coefficient, or eta, and step 3 is the radius of the tube, r. Now, we might not know the exact powers these factors are raised to, say A, B, and C, but because there are exactly 3 variables with dimensions, dimensional analysis works perfectly to help us derive that relationship.
But here is the foundational limit. In basic mechanics, we only have 3 foundational dimensions to work with, right? Mass, length, and time. Mathematically speaking, when you equate the powers of m, l, and t on both sides of an equation, you're generating exactly 3 equations. And as basic algebra tells us, with 3 equations, you can only solve for a maximum of 3 unknown variables. It's that simple. If a physical quantity depends on 4 or more different factors that have dimensions, dimensional analysis completely stalls out. It is a hard mathematical roadblock. You simply don't have enough equations to find that 4th power.
Next up is Section 4, Trigonometry and Log Functions.
Now think about these messy, incalculable roadblocks. Take a thermodynamics formula for work. W equals 2.303 nRT times the log of V2 over V1. Or really, any formulas containing the sine of theta, cosine of theta, or e to the power of x. Dimensional analysis completely breaks down when facing these. Why? Well, because trigonometric, logarithmic, and exponential functions are inherently dimensionless. If your physical phenomenon relies on an angle or a natural log ratio, dimensional analysis is just going to draw a blank. It cannot derive any formula that features these complex functions. No way.
And finally, Section 5, the mystery of scalar versus vector quantities.
So consider the fundamental difference between scalar quantities, which only possess magnitude, and vector quantities, which possess both a magnitude and a specific direction. Dimensional analysis gives us absolutely 0 clues about whether a derived quantity has a physical direction. None. You could be looking at a dimensionally perfect formula, flawlessly balanced in terms of mass, length, and time, and still have absolutely no idea if you're dealing with a scalar or a vector. The entire method is completely blind to directionality. Before we wrap up, I do want to mention one last technicality, just to make sure your exam notes are perfectly comprehensive. Dimensional analysis cannot derive exact relations if the formula consists of multiple terms added or subtracted together. Think back to our earlier example, s equals ut plus 1/2 at squared. You see, dimensional analysis is fantastic for deriving formulas that rely purely on multiplication and division. But the very second you throw an addition or subtraction sign in there to separate different terms, the derivation method fails. It just kind of falls apart and can't build that structure from scratch. So I want to leave you pondering this final kind of provocative thought. If dimensional analysis can't tell us everything, is it still useful today? And the answer to that is a resounding absolute yes. For sure. Despite its kryptonite, its inability to spot dimensionless constants, that strict 3-variable mathematical limit, and its total blindness to vectors and trig functions, it still remains a profoundly powerful foundational tool for literally any physicist. It is your first line of defense to check the accuracy of your work. As long as you keep these limitations clearly in your mind, you'll be able to wield this mathematical superpower perfectly. Keep learning, analyzing, and I'll see you in the next explainer.